Hydrocarbons. Hydrocarbons are those class of organic compounds which are only made up of carbon and hydrogen. Let us see first their classification. Hydrocarbons are divided into three major categories. The hydrocarbons are divided into three major categories. The first one is for saturated hydrocarbons, which will be having only carbon-carbon single bonds. Then we have unsaturated hydrocarbons, which contains at least one carbon-carbon double or carbon-carbon triple bond. And the last in the category are your aromatic hydrocarbons, which includes benzene or benzene-like aromatic compounds. So we have mainly the hydrocarbons of these three categories. Saturated, again, we have only alkanes in this category. We also include cycloalkanes, alicyclic one under the same category. Unsaturated includes your alkenes and your alkynes, and aromatic includes your benzene and benzene derivatives like naphthalene and etc. So let us see now, take one of these, all of these one by one. We will first take alkanes. The alkanes are the saturated hydrocarbons. They have a general formula of CnH2n plus 2. So they are having all carbon-carbon bonds are single bonds. There is no double or triple bond in these compounds. And they are least reactive organic compounds. They are commonly called paraffins, which means least affinity, because they have no polarity of in any of the CC or CH bonds which they have. The most common examples we include are like your methane, ethane, etc. One thing which is most important to note in these compounds are that in these all carbons are sp3 hybridized. They all are tetrahedral and are having the angles of 109.5 degree. Now let us see the nomenclature and isomerism. Nomenclature and isomerism in alkanes. See, we know that we call alkanes with a simple name alkanes only. We know that they can have a long chain of the carbon-carbon single bond. Like if we have, suppose, this hydrocarbon alkane, we will call it, since it contains 5 carbon, we will call it what? Pentane. If we have any of the side chains which is there of a carbon which is there on the chain with the in place of a hydrogen, we call it a substitution group. We can write it like this. Suppose we have this one. So this is called a side chain or branching. We treat it as a side chain or substitution group. We give the lowest locant or the number possible to this side chain, and that is how we will number the carbon atoms from the side which will be giving this particular side branch or any of such ones the lowest possible number. So we will call it 2-methyl. Why methyl? Because this is what is the methyl. We have already done this kind of nomenclature in the previous chapter, which is the general basic concepts of organic chemistry. So we know that we call it, these substitutions are called alkyl, so it is 2-methyl butane. So this is, or it is also called, since this group is called iso in the common nomenclature, we will call it what? Isopentane. But isopentane will be, remember, it's common name, not an IUPAC name. Similarly, if we have, suppose, more than one of these side chains, like suppose this is the carbon chain we are having, and this is what we are having in this case. In this, we will number the carbon chain from left hand side. Now we are having how many methyls out of this chain? 3. So we'll number them 2, 2, 4, tri-methyl. We'll put word tri to indicate there are 3 such methyl groups. and then we will write down hexane. So this is how we name the alkanes, because we can't have any much more variations, typical variations in this, because they are simple hydrocarbons. They are having what saturation, they have all single bonds, and there can't be any other group except these side branches in these alkanes. The isomerism. The alkanes shows mainly two types of isomerism. One is chain isomerism, another is position isomerism. So these are the two isomerism which it shows. Both are in the category of structural isomerism, remember. Though some alkanes also shows if they are having what all four groups attached, different group is attached to the to a particular carbon atom, they will be showing what a very other special type of isomerism, which is also called optical isomerism. And there's one more other type of isomerism which is very, very exclusive to these alkanes, and which is called conformational isomerism. We will be dealing with it later on. Let us first see how the chain and the position isomerism are shown in this. Like suppose we have this N-hexane, or we have a simple hexane, it is of a 6 carbon. We can have a hydrocarbon with the same formula, but which is having a one longest chain of 5 carbons, but 1 methyl as a substitution. So we call it 2-methyl pentane. And remember, these two are the chain isomers of each other. In a very similar way, remember, if I places this methyl from changes its position from carbon number 2 to carbon number 3, like this one, this is 3-methyl pentane. Remember, these two, this one and these one are chain isomers of each other, but these two among with each other are position isomers, because in this the position of the side chain has been changed. So these are the two basic type of isomerism it shows. The conformational we will be doing later on. Now let us see the preparation methods of alkanes. The first is from unsaturated hydrocarbons. This is done by hydrogenation, which is a sort of a reduction process. In this, what is done is, even if we take any alkene or alkyne, they are reacted with any alkene or alkyne is reacted with hydrogen presence of platinum or palladium or nickel catalyst, which actually are very strong, they have very good affinity for the hydrogen. So they absorb hydrogen on their surfaces, which leads to the breaking of the HH bond, and due to which the hydrogenation of the alkenes or alkynes takes place, which leads to the formation of what alkanes. So with this method, ethene gets converted into ethane. Even if we have ethine, remember we will be using 2 moles of hydrogen gas, platinum or palladium or nickel, any one of these catalysts are used, and what we get is an ethane, even from ethine. What you need to remember is this reaction with platinum or palladium takes place at room temperature, but with nickel it takes place at a much higher temperature and pressure. So this is a simple hydrogenation process of converting unsaturated hydrocarbons to saturated hydrocarbons. The second method of preparing the alkanes is from alkyl halides. In this we have basically 2 methods. By 2 methods we can convert alkyl halides into the alkanes. The one is a very simple reduction process by reduction, and the best way to do is any alkyl halides. Remember, the halide here is chloride or bromide or iodide. So they, when reacted with zinc in presence of dilute HCl, what happens is RH is obtained, alkane is obtained in this process. Along with this with this what happens is the hydrogen in this gets as it actually is replacing out the X out of this, and this is how this reaction takes place. So we can use the dilute HCl or any other dilute mineral acid which gives us this reaction. Now what happens in this cases, like let us take the examples, like if we have ethyl bromide, zinc dilute H plus is going to give us what, CH3 plus HBr. If we have suppose CH3, CH2, CHBr, CH3, zinc any dilute H plus, CH3, CH2, CH3 plus HBr. So this is how we can convert the alkyl halides into alkanes. The next method to prepare alkanes from alkyl halides is by Wood's reaction. It's a name reaction, yes, by Wood's reaction. In this, the alkyl halides are reacted with what? Sodium in presence of dry ether. 2 molecules of these alkyl halides combines with 2 molecules, or 2 moles of alkyl halide combines with 2 moles of sodium, and what we get is RR plus NaX. So this will be twice of this. So what happens is that the carbon chain of the alkyl halide becomes double, and that is what is most interesting, that it's a step-up process in which the number of carbon in the product is just the double of what we were having initially in the form of alkyl halides. So if let us take example, if we have ethyl bromide and if we react this with sodium in presence of De means dry ether, what happens is we get the chain gets doubled, so the 2 carbon becomes 4 carbon. So we will be getting what butane along with 2 moles of sodium bromide. So this is what we get if we have the ethyl bromide. So this is a very interesting method in which the step-up process, the carbon chain is becoming double, but the only problem with this process is that we can't prepare odd carbon alkanes with this. The reason is because every time the chain is getting doubled. And even if we are trying to prepare take 2 different alkyl halides in order to prepare the odd carbon alkanes, we will not be able to get what the pure mixture of that particular hydrocarbon, because what we get is we get the mixture of different hydrocarbons, which we again have to separate out in order to get odd carbon alkanes. There's one more limitation of this reaction, that we cannot prepare methane out of this reaction. We cannot, because 1 carbon alkane cannot be prepared by this. This reaction proceeds by free radical mechanism, remember. Because of the sodium, the mechanism used by this reaction is the free radical mechanism. Next method of preparing alkanes is from carboxylic acids. We again have 2 different methods in this category. The first is called by decarboxylation. It is decarboxylation, the word means the removal of the carboxylic group, the COH group. Now it's a step down process in which the product formed is having 1 carbon less than what initially the reactant was having. In this, what we do is any the carboxylic acid taken is heated with soda lime, the sodium hydroxide and calcium oxide, and due to this what happens is alkane is obtained along with sodium carbonate and water. So this is what is the main thing which we must note, that if the acid was having n number of carbon atoms, the alkane formed is having n minus 1 number of carbon atoms in the alkane. So it's a step down process. So one of the most important process to decrease the number of carbons, because the carbon in the form of the carbonyl or carboxylic group is lost in the form of carbonate ion. So if we have suppose propanoic acid and we take sodium hydroxide, calcium oxide, we heat it, what we get is ethane out of this, sodium carbonate plus water. So we get ethane out of this, from propanoic acid. So this is one of the most interesting methods of a step down process. The second method from carboxylic acids is by Kolbe's electrolysis. Kolbe's electrolysis. In this Kolbe's electrolysis, sodium salt of carboxylic acids in aqueous medium on electrolysis gives alkanes with twice of n minus 1 number of carbon atoms at anode. So that's most interesting. And hydrogen gas at cathode. Now let me explain you this. I'm just repeating this one. The sodium salt of carboxylic acids in aqueous medium on electrolysis gives alkanes with twice of n minus 1 number of carbon atoms at anode and hydrogen gas at cathode. Let us take this example. Let us take, we are having what? Sodium propanoate. Now this sodium propanoate, when it is subjected to electrolysis, it gives propanoic acid and sodium ion. Now at anode what happens is this propanoate ion comes and it gets oxidized to what? Propanoate free radical, and it loses one electron. Now this propanoate free radical gets changed to what? Ethyl radical, and it loses one CO2 molecule. Now two such ethyl radicals combines together to form butane. So remember, if the acid is having n number of carbon atoms, the alkane formed at anode will be having twice of n minus 1 number of carbon atoms. And at cathode what happens is, of course, sodium ion goes there to accept electron, but this reaction is not possible because to accept electron, this tendency of accepting electron is more in case of water. So water accepts electron and gets reduced to what? Hydrogen and 2 OH minus ions. So this is how we get what? Hydrogen gas at cathode, and the butane with twice of, or any alkane with twice of n minus 1 number of carbon atoms at anode. Now let us discuss the properties of alkanes, and then the first comes are their physical properties. In this, let us first discuss their state. Remember, C1 to C4 alkanes are gases, C5 to C17 are liquids, and C18 or above are solids, waxy solids. Remember, but one of the most important things, whether they are gases or liquids or solids, remember they all are colorless, without any smell compounds. They don't have any color, they have no polarities in their bonds, so that is why they are having least affinity, and that makes them what? Least reactive. That is what we call them paraffins. So that's their basic state is. Now let us talk about their melting points and boiling points. Now out of this, let us first talk about their melting points. Remember, melting points increases with increase in carbon atoms. Of course, because as the chain grows, the more it becomes more, the melting point increases. But what we find very strange thing is this, that in alkanes with even number of carbon atoms, their melting points is found to be more than the melting points of its neighboring odd carbon alkanes. So what we find is that if we plot a graph between here we have, let me draw a little bit bigger one. So if we have a number of carbon atoms, and if we have melting point, what we find is it's always is like this. So it is at 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we find is the alkanes with even number of carbon atoms are having their melting points more than their neighboring odd carbon alkanes. The reason is because, what is the reason behind this is, the reason is the more compact packing. See, if we have, suppose this is your normal butane, we have one molecule and gets more easily compactly packed with the other molecules. So the packing is more compact in case of even number of carbon atom alkanes. If it's an odd one, what will happen is they will have a lot of steric hindrance, and that is why the packing will not be compact, and as a result their melting points are low. This is one of the most important things, striking feature. Now let us talk about their boiling points. Remember, boiling point always is directly proportional to molecular mass, and is therefore as the carbon number atoms increases in the hydrocarbon or alkanes, the boiling point increases. But if we are talking about isomeric species, we need to know that the boiling point is directly proportional to surface area. And that is why if we have, suppose N-pentane and we have, suppose isopentane, and if we have neopentane, the boiling point will be in this order. The reason being, this is having the largest surface area, and this being spherical in shape, it is having the least surface area. So that's the second most important thing. Then we have, let us talk about their the third point in the physical properties is their solubility. Now solubility, remember, they are insoluble in polar solvents like water, etc., but completely miscible with organic or non-polar solvents. So that's the most important thing we have. Now let us see the chemical properties of alkanes. See, we know that in alkanes we don't have any polarity in any of the CC or CH bonds, so that's why they are having no sort of polarities, and that is why we call them having compounds with the least affinity or paraffins. Now, so they show mainly the substitution reactions. We want to introduce anything if on these compounds, we have to replace hydrogen. That is why they are called, and their main characteristic reactions are their substitution reactions. Moreover, because of the non-polar nature, all substitution reactions also are free radical reactions. Now, let us see these substitution reactions. Remember, in this, the hydrocarbon, which whatever we are having, its hydrogen can be replaced by any halogen or by nitro group or by sulfonic group. This is called halogenation, the introduction of halogen group. And if NO2 is introduced, it's called nitration, and if sulfonic group is introduced, it's called sulfonation. We will be discussing, let's take an example of how the halogenation is done. The best example is the halogenation. See, the halogenation is done either at a very high temperature of nearly around 500 degrees Celsius, which leads to the homolytic fission of the Cl-Cl bond, or in the presence of diffuse sunlight or ultraviolet lights. So when the ultraviolet UV lights are used, the product formed is CH3Cl plus HCl. How this reaction takes place, we need to know the mechanism. Let us see the mechanism in this case. First, what happens is, it's a sort of a chain reaction. So the first step is chain initiation. In the chain initiation step, what happens is, the UV light or the diffuse sunlight or high temperature leads to the homolytic fission of the CCl-Cl bond because it is non-polar in nature, and this results in the formation of chloride free radical. Now this chlorine free radical, then again, since the first step is how the free radicals are formed, then the second step includes propagation. Now how the reaction proceeds further? This radical combines with methane, and it leads to the breaking of the homolytically breaking of the one of the CH bonds, which results in the formation of methyl radical and HCl. Now this methyl radical again reacts with one chlorine molecule, leads to its homolytic fission, giving you what CH3Cl, and the again is one Cl radical is formed, and this Cl radical will again show these type of reactions. So what we can make out from these two steps is that the chain initiation step is a step in which the free radicals are formed from the normal molecules, so that the free radical reaction starts. The moment what we find is what is the propagation step, in which a free radical combines with one of the reactant to form a product, another product, and another free radical, which again combines with one of the reactant to form another product and another free radical, and this is how the chain reaction continues. Now what happens is, where these reactions stops? These reactions stops at a stage which is called chain termination. Chain termination is the third step. Now in this what happens is, whatever the radicals we have are there in the reaction mixture, they combine with each other, because as their concentration increases, the probability of collision between these radicals gets increased. So what we get is the product like ClCl. Even if we have CH3 dot to methyl radical and a chlorine radical, it will give us methyl chloride, and it will also give us small amount of, when two methyl radicals will combine, it will give us, yes, definitely ethane also. The formation of ethane is an indication that whatever the mechanism we are supporting for this reaction is very, very correct, because we actually also we get small amount of ethane in this reaction. We can do this chlorination, we can do bromination, yes, by the of the alkanes by this method. If you are having CH3 chlorine sunlight, we get CH3CH2Cl plus HCl. We can do iodination also. See, remember, bromination is same. But the problem comes when we are doing iodination. What happens is it leads to the formation of methyl iodide plus HI, of course. But due to the HI being the strongest halogen acid, this reaction becomes reversible. We can avoid the reversibility of the reaction by letting it to take place in presence of the species, the oxidizing agents, like we can have nitric acid or iodic acid, because this nitric acid will react with HI formed, and it will form what, NO2 plus I2 plus water. And if we are having, suppose, iodic acid, it will combine with HI, it will form H2O plus iodine. So what happens is, if we know from the Lee-Chatter's principle, one of the product is removed, the equilibrium shift towards forward side, and this is how we can avoid the reversibility of this reaction. Now let us see the second reaction, which is their combustion reactions. We know hydrocarbons, since they are having only carbon and hydrogen, they show combustion reaction. They get oxidized when reacted, when heated in oxygen, they catches fire, and they gets converted into CO2 and H2O. Like we have a methane, which on combustion shows a form CO2 and H2O, and the energy release with per mole of methane is minus 890, the 890 kilojoules per mole is the energy released in this process. So, and we must know, and we already know from the junior level, that as the carbon atoms increases in the alkane, the energy release also gets increased. But also remember, if we are allowing this combustion reaction to take place in almost in an incomplete manner, this same combustion reaction leads to the formation of coke and water. It forms solid carbon coke, black carbon. Now let us see that the alkanes also shows controlled oxidation, which is basically also called catalytic oxidation. The same methane and oxygen in presence of copper at 350 degrees Celsius and 100 atmospheric pressure leads to the formation of methanol. Same methane and oxygen in presence of manganese oxide and on heat forms formaldehyde and water. And the same methane and oxygen in presence of manganese acetate as an oxidizing agent leads to the formation of acetic acid. Also, you need to remember that if suppose we are having an alkane which is having a tertiary CH bond, a carbon hydrogen which is a tertiary hydrogen, this on oxidation by KMnO4 directly leads to the formation of tert butyl alcohol, or we can say it is tertiary it is 2-methyl propane toluol tertiary alcohol. So it leads to the formation of tertiary alcohol. The next reaction of alkanes is the isomerization reactions. In these reactions, when N-alkanes are heated with the anhydrous aluminum chloride and HCl, they get changed to what? Branched alkanes. Let me give an example of this. If suppose we are having N-pentane, straight chain alkane pentane, and it is heated with anhydrous AlCl3 in presence of HCl, what we get is isopentane. Isopentane or 2-methyl pentane or 2-methyl butane. So this is what is called isomerization reactions, in which what we find is both the reactants and the products are basically isomers of each other, and alkane shows this isomerization reaction. Next reaction of alkanes is aromatization reaction. This is also called reforming. This reaction is also called reforming. In this, the alkanes, straight chain alkanes with carbon number 6 or more when heated, like let me give an example of N-hexane. So this is CH2,4 and CH3. So this is N-hexane. Now this N-hexane, when heated in presence of vanadium oxide or chromium oxide or molybdenum oxide, any one of these at around 500 degrees Celsius, 10 to 20 atm pressure, they results in what? In the formation of benzene. That's very important to note, that this leads to the formation of, this is basically a dehydrogenation reaction. The hydrogens gets removed and we get C6H6, a benzene in this. If suppose we take in the same very similar situation, if we take N-haptane in place of hexane, in a very similar situation, we will get toluene as the product, whereas the N-hexane gives us benzene by this reaction. So this cyclization, not only is this is not cyclization, this is basically the formation of aromatic compounds. That's why this is called aromatization or reforming, in which the open chain alkanes, straight chain alkanes are converted into the aromatic compounds. Then the next reaction of alkanes is the reaction with steam. The alkanes with steam, in presence of, when heated with steam in presence of the catalyst like nickel at around 1000 degrees Celsius, results in the formation of carbon monoxide and hydrogen gas, which is together is called a water gas. It's a very good method of preparing hydrogen gas, as well as this water gas is being industrially then used to form methanol and many other organic compounds. The next reaction of alkanes is pyrolysis. It's breaking down of the higher hydrocarbons to smaller hydrocarbons is called pyrolysis. This is mainly done by heating. What we do is by heating we decompose a higher hydrocarbon into a smaller hydrocarbon, and when it is specifically done for alkanes, it's called cracking. So cracking is pyrolysis of alkanes, in which the higher alkanes are decomposed to give smaller alkanes and alkenes. Let me give you an example. If suppose we have C6H14, this is what we have is hexane. Now this hexane on heating at 500 degrees Celsius gives us all possible different products, because this results in the form breaking down of not only the CH bonds but also the CC bonds. So that's why what we get is, we get C6H12 plus hydrogen gas, we get C4H8 plus, we also get C2H6. We also get along with this C3H8 plus C2H4 plus CH4. So all these sort of different products are formed, and the breaking down of this bigger hydrocarbon chains of alkanes to smaller one is called cracking of alkanes, and basically it's a pyrolysis. It is mainly being used to what? Decompose or bigger higher hydrocarbon chains into smaller ones. Like what we do is if we take dodecane, it's broken down into hexane and heptane, and all those the different products can easily be hexene, sorry. And what we get is that we can prepare petrol or other type of gasoline products by taking the long higher alkanes or higher hydrocarbons. So this is a very useful method of preparing smaller, more useful hydrocarbons. Conformations. Conformations are the special type of isomerism. It's a special type of stereoisomerism shown by alkanes. It is the isomerism which arises in inorganic compounds or in compounds due to the rotation along carbon-carbon single bond. And each isomers which we get out of this are called conformers or rotamers. Let me explain to you. Let's take an example of a very simple molecule, ethane. Now, in this ethane, what happens is, since these two carbons are joined to each other through a normal single sigma bond, the rotation of rotation along these carbon-carbon bond is possible, and as a result, what happens is the three-dimensional spatial arrangement of the three hydrogens which they are having can change. And this can result into the formation of different types of three-dimensional structures which are called conformers or rotamers. Now, in order to represent those three-dimensional systems, we use two ways of representing those three-dimensional structures. One is called Sahor's formula. In this, what we do is we draw this ethane molecule in the form of a horse, which is almost just like this. So this is one of the forms of which is called Sahor's formula. In this is first carbon, this is second carbon, which is first carbon is having 3 hydrogens and second is also having 3 hydrogens. In this type of three-dimensional representation of the molecules is called Sahor's formula. What we can, or Sahor's projection formulas. In this, what we can easily make out is that this hydrogen is actually on a very similar line to the hydrogen which is there on the second carbon, and as a result these two hydrogens are eclipsing each other. In a very similar way, these hydrogens and these hydrogens are eclipsing each other. Now, since they are very close, there what happens is there will be a lot of interelectronic repulsions about the electronic clouds between these two hydrogens. As a result, this particular type of three-dimensional arrangement of the hydrogens on the two carbons will be having high energy. Now, this type of, therefore, conformation is called eclipsed conformation. Now, what happens is due to this molecule will on its own, these carbons will show rotation like this, and they will get changed to this type of system in which what we find is these hydrogens will be maintaining the maximum distance from each other so that the interelectronic repulsions will become what? Minimum. And as a result, this type of the three-dimensional system of the ethane molecule will be having lower energy and more stability. So whenever we pick up ethane molecules, we'll be having ethane molecules in both this eclipse form and in this form. And this form of this eclipse molecules is called staggered conformation. So this is eclipse conformation, this is staggered conformation, and which is having a lower energy. The staggered conformation is having a lower energy. The reason being there is no eclipsing of the hydrogen, so the interelectronic repulsions are minimum. The energy difference between the two forms is very, very small. It's almost 12.5 kilojoules per mole, which is very, very less, which they easily acquire due to the intermolecular collisions. And as a result, that's why that makes the separation of these two types of different three-dimensional arrangement of the same molecule not possible to be separated into independent species or isomers. But yes, they exist in a mixture of the ethane sample. Now, these two types of conformation are also represented in one more form, which is called Newman's projection formula. Let me write it down. Newman's projection formula. In Newman's projection formula of this ethane, what we do is we always draw carbon number 1 in this form, in the form of this, from a point we draw 3 lines diverging, making an angle of 120 degree with respect to each other. And now the dot of where from these lines starts represent carbon number 1, and then we draw a bigger circle which represents carbon number 2. Now this carbon number 2 is also having what these 3 types of lines. Now these are the 3 hydrogens. each of these two carbons are having. Now this kind of molecule, this kind of three-dimensional system or the Newman's projection formula is representing what? Your same sawhorse eclipse structure. Not this one, this is staggered. This one. So this is the same one, and you can make out that this hydrogen and this hydrogen, they are just on the same line. That's why they are eclipsing each other, and they will be having a lot of interelectronic repulsion as a result. This particular type of conformation will be having high energy, and this is called eclipsed. In a very similar way, when this is rotated to 60 degree only, why 60 degree? Because by rotating it to 60 degree, this hydrogen will come on this other side, and we always rotate the carbon number 2. So what we will get a new Newman projection structure of three-dimensional formula. It will be like this. Now this is representing your staggered conformation. And from here you can easily make out that since these distances are maximum and all the hydrogens are at a maximum distance from each other, the interelectronic repulsions are minimum, and therefore stability is the highest. So therefore ethane has two conformations, eclipsed and staggered, and they differs by an energy of 12.5 kilojoules per mole. Staggered is more stable, having lower energy, and eclipse is having higher energy.